So, welcome again to the new lecture of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we were doing in the last class. So, let me just go to the next page. So, in the last class we were looking at phase transitions in ferroelectrics. So, we started our discussion with second order phase transition. Where we found that in the free energy expression you have three constants A, B, C, and B and C being positive, but A changing its sign across Tc. So, of course, these free energy plots can be plotted by choosing appropriate values of A, B, C. So, when we plot them, what we find is that when you plot free energy as a function of polarization, for A being so A could be changing its sign from positive to negative. So, basically what happens is that in the first case your A is positive when it is, so when the temperature is, so this A is greater than 0 at T greater than a transition temperature called as Tc, and when A is negative there are two maxima. So, this is at T less than Tc when A is negative, and then in between, of course, since A changes its sign, which means as a function of temperature it must be 0 somewhere, and it turns out it is 0 at T is equal to Tc when A is equal to 0. So, this is a second order phase transition, and when you plot polarization as a function of temperature, because the parameters are the function of temperature as well. So, when you plot polarization as a function of temperature, it shows a gradual change up to a temperature Tc. So, this is polarization, and when you plot susceptibility, susceptibility shows a behavior like this at Tc. This is 1 over chi. It has different slopes on the two sides of the transition, but there is a there is no abrupt change in polarization or in susceptibility at transition temperature, and this is also manifested, as we will see, in the entropy. The entropy also does not change in the second order. There is no abrupt change in the first derivative of free energy, that is entropy, but the second derivative changes abruptly. So, this is basically second order transition. And then we also looked at what is first order phase transition. In the first order phase transition, what we saw was that now we took B less than 0, C greater than 0, and sign of A changes, okay, and there we see that there is a range of temperature between which the free energy curve remains unconventional. So, when you plot now free energy as a function of pressure polarization, so G as a function of polarization. So, at high temperatures, let us say at high temperatures the polarization plot G is, so this is at T greater than a certain temperature Tc, and it shows one minima, okay, which is the unpolarized state. And then when you go to, so this that is when A is greater than 0. Now, when you plot at lower temperature, so this is let us say T is equal to T0, but it is less than Tc. So, at this temperature A is negative and it is less than, and at T is equal to T0, which is lower than Tc. At Tc, what happens is that at Tc we have a situation in which we have so this is let us say at T is equal to Tc when A is equal to 0. And this is the situation when we have three minimas. So, you can see there are two minimas corresponding to the polar phase and one minima corresponding to the non-polar phase. So, this suggests that we have one non-polar phase in coexistence with the polar phase between the temperature Tc and T naught, and it is only at T naught the material stabilizes into a perfectly so this is polar state, and this is manifested in polarization in a different way. So when you plot polarization as a function of T, in this case what we see is that the polarization decreases and then it goes abruptly equal to 0 at Tc, okay. But the susceptibility shows a different kind of behavior. So now when you plot susceptibility, so this is polarization, let us say that red one is polarization, and the green one if I plot as susceptibility, susceptibility shows a discontinuity at temperature Tc, and if you plot this extrapolation of this, this is the temperature T naught. So this is the range Tc T naught minus Tc minus T naught, within which you have coexistence of these two phases. In contrast, if you look for if you look for second order, in that case you can say Tc is equal to T naught, right. But in this case you have T naught and Tc which are different temperature, T naught being lower than the Tc. Now what is this manifested in? This is manifested in a discontinuity in susceptibility at Tc and sudden drop of polarization at Tc. So polarization has a finite value at this point and suddenly it drops to 0. So which means there is a discontinuity, right. So this is called as first order phase transition. This is also manifested in as we will see, discontinuity in the first derivative, that is del G by del T, and which is nothing but minus of del G by del T is entropy. So in the second order phase transition, it is the second derivative that is discontinuous, whereas in first order phase transition the first derivative is discontinuous. That is the fundamental difference between the two. So we did some analysis of second order phase transition and we looked at the susceptibility parameters. Now let us look at the first order phase transition again in a little bit more detail. So we get back to first order phase transition. So for the first order phase transition, we first see the change in entropy. The change in entropy is nothing but S minus S naught. This is equal to minus of half P square dA over dt if you ignore the higher order terms, sorry, not small t, but it should be capital T. Now since polarization is discontinuous at, so we know that polarization shows a discontinuity at if polarization shows a discontinuity at, so this is minus of P square, then obviously entropy will also show discontinuity at, so basically we will have entropy also showing discontinuity at Tc, and this is what is basically first order transition. In the second order, what happened was, if you recall second order, in second order the entropy will, the term will be the same, minus of half P square dA by dt, but there P is continuous, which means S is continuous. Now when you take the derivative of this, you take del S by del T, which is, so Cv will be equal to del S by del T, which is minus of half del 2 G by del T2 del T2. Now P square actually becomes discontinuous. So P square is discontinuous, slope of P square, so slope of P square is discontinuous at Tc, which means your Cv is discontinuous. So you see here, so basically in this, since there is a change in entropy, there is a discontinuity in entropy, which means you have latent heat of transformation. There is, since entropy is continuous, there is no latent heat involved. So, in some sense you can say the first order transition is more of a destructive transformational where a lot of rearrangement takes place, just like liquid solid kind of transformation, whereas in second order the transformation is more gradual. As a result, the free energy curve will also show some sort of continuity in two phase regions and the slopes being equal in the both regions. As a result, there are no discontinuities in entropy or the free energy. There are no sudden changes in the free energy. As a result, there is no sudden kink in the or discontinuity in the entropy. So, this is what it is in terms of phase transition. If you look at first order in a little bit more detail, if you want to work out the susceptibility parts in both regions, then we know that first condition is that at equilibrium we can take E to be equal to 0, and we know that del G by del P at T is equal to E, this is equal to 0. So, if P is not equal to 0, in that case you can write this expression as A plus B P square plus C P 4 to be equal to 0. There is the first equation that you will get. Secondly, at T is equal to Tc, GTc will be equal to G naught Tc, and this will be equal to 0 as well. The free energies of phases should be equal. So, as a result, we will have G, we can write the G expression as half of A P square at Tc plus 1 by 4 B P to the power 4 plus 1 by 6 C P to the power 6 and so on and so forth, this being equal to 0. So, this will become basically half of A P square plus 1 by 4 B P 4 plus 1 by 6 C P. If you ignore the higher order terms, using these two equations you can determine the polarization as minus of polarization square will be minus of 3 by 4 B divided by C, and A will be nothing but 3 divided by 16 B square divided by C. So, basically you will have polarization as plus minus square root of 3 by 4 B divided by C. So, since we know that, since we have assumed in the beginning that B is less than 0, if B is less than 0, then P becomes discontinuous at T is equal to Tc. So, now we need to consider the susceptibility before and above Tc, and if you do simple analysis at above Tc, A is greater than 0, okay, and A is equal to 1 over chi A. So, in this paramagnetic region it will remain the same as earlier, it will be C divided by T minus, you can say theta was taken as earlier, but this will be C divided by T minus T naught. This is the paramagnetic susceptibility. So, if you look at the plot of susceptibility 1 over chi, this is the, so this will go like this and it will go up to T naught, this is Tc, where this T naught is little smaller than Tc. It's a, and then above Tc, below Tc, we can work out what is del G by del P. This is equal to E, and this will be AP plus BPS P cube. You can write P as PS below Tc, but that is something. So, 1 over chi B will be equal to del E by del P, and this will be equal to A plus 3B P square plus 5C P 4 and so on and so forth. So, if you now just so 1 over chi B will be equal to A plus 3B, we already know the value of P square, which is equal to minus of 3 by 4 B by C plus 5 into C. So, this becomes 5 into 3C into A by C. You can also replace B in terms of A, because remember this was the value of A, this was the value of P square. So, if you make the proper substitutions, you can get this in terms of 5 into 3 into C into A divided by C. So, this will turn out to be 4A. Okay. So, in this region it will go as 4A. So, that is what this susceptibility will be. So, in the first case you will have a slope of 4 and the second case you will have slope of 1. So, you just have to replace the value of A there. So, it will become something like this, alright. So, this is chi in temperature T less than Tc and this is chi in temperatures greater than Tc. So, this is what the variation of. So, in general if you just wanted to look at the phase transitions, so ferroelectric phase transition, so as I said that second order phase transition is more common for materials like Rochelle salt and KH2PO4 etc., whereas first order phase transition is more common in materials like barium titanate etc. Perovskite materials show generally first order phase transition. If you generally wanted to know about the phase transitions, the order of, as I said, the first order phase transition has a discontinuity in the first derivative of free energy. Second order phase transition will have a discontinuity in the second derivative of free energy, the first derivative remains continuous. So, if you plot this now in a general sense, so let us say we make a column of first order and then we make a column of second order, and let us just make the plots of these quantities. So, let us say okay. So, in the first one we plot G versus T. Okay. So, when you plot G versus T, so let us say you will have variation like this. So, this is the temperature Tc at which the transformation is occurring. So, you can consider this being as if this is the free energy plot of height one phase, let us say G alpha, and this is the free energy plot of another phase which is G beta. So, you will see that free energy plots intersect each other at some point. Sorry, I have plotted in a little, just one second. It should have been. So, this is the free energy plot of one phase and this is the free energy plot of another phase. So, the first phase's plot continues in this region in this fashion. So, this is G alpha and the second phase's plot will go in this region as which is G beta. Okay. Alpha beta could be considered as ferroelectric phase and paraelectric phase. So, you can see in this below Tc alpha is stable and above Tc beta is stable, right. So, this is G beta. So, this is first order phase transition. In the second order what you will see generally is that something like this, the free energy will be little bit sort of continuous along transition. So, let us say if this is the transition temperature Tc, the free energy will show sort of, they will have common slope at this point, whereas in this case the slopes are different, right. Now, if you plot the entropy as a function of temperature, let us use a different color. So, let us say we plot entropy S versus T as a function of temperature, we will see that in this case entropy is nothing but del G by del T. So, in this case the entropy will show a discontinuity, right. So, this is delta S which is correspondent to latent heat. So, the slope will be given as Cp specific heat, and in this case we will see a sort of variation in the slope. So, something like that. So, you will have, there will be no discontinuity, but the slope will change and the slope again will be C, right, the specific heat. Now, coming to the next one, if you now plot the C at this transition, it will be a massive divergence in specific heat at Tc, right, whereas in this case if you plot C versus T, the C versus T will show a discontinuity like this. So, there will be a discontinuity but in this case we will have it nearly goes to infinity. So, there is a huge, so sort of tending to reach infinity or very high values. So, this is what you see. So, in this case, in first order you see a discontinuity in entropy or first derivative of free energy. So, this is del G by del T, if I just use the S, which is del G by del T. This is minus of del 2 G by del T 2. This is, so right, first derivative discontinuous in first order, second derivative discontinuous in second order. So, this is the whole summary of phase transitions of ferroelectrics. If you are really interested to know about ferroelectric phase transition, in fact the Landau theory, I will recommend you to a very good paper. So, so this is the paper which is in journal Advances in Physics. So, this is 310, so volume 3 issue 10 page 85 to 130 1954 by A.F. Devonshire. Beautiful paper. This narrates the whole phase transitions in different kinds of phase transitions in ferroelectrics. So, we unfortunately cannot go into so many details because of limitation of this course, but I hope this has given you a brief idea about what kind of phase transitions that occur in these materials. Now, let us go into the next topic of ferroelectrics. Having seen what kind of phase transitions occur in ferroelectrics, now let us look at how do ferroelectric materials switch. What is the reason of hysteresis in the ferroelectric materials? So, as we saw earlier that, so here we will look at ferroelectric switching. So, ferroelectric switching basically is manifested in, as we saw earlier, you make a plot between charge and electric field or charge density versus electric field or polarization versus electric field, and the plot is something like this. You can see sort of a something like this. So, this saturates at high fields, so something like that. And so, what happens in this ferroelectric is, you, as we saw earlier, you have a hysteresis. The polarization at high fields is spontaneous polarization, polarization at zero field is remanent polarization, and the values of these spontaneous polarization and remanent polarization, they are equal and opposite to each other, and then polarization becomes 0 at a field called as coercive field, which is depicted at plus and minus EC, which are symmetric with respect to each other for an ideal system. Now, the question is, why do these ferroelectric show, and this area under the curve, by the way, is nothing but the energy that is spent in switching. So, energy spent in switching will be P into E, right, energy per unit volume. So, this is nothing but mu E divided by volume. So, per unit volume. So, this energy is basically spent in switching. So, the question is, why do we get this kind of behavior? So, in ferroelectric what happens is that, so this we can write area under the hysteresis curve. Now, what happens in these ferroelectrics is, when you start from a virgin ferroelectric which has never been switched before, you start generally from origin. The polarization of a virgin ferroelectric is generally 0, polycrystalline ceramic, and what happens is that initially when you start switching the ferroelectric, it switches in sort of a linear fashion. So, up to point B, ferroelectrics are nonlinear ceramics, right, but in the beginning from A to B the polarization changes as a function of electric field in a linear fashion. So, this is AB. Now, when you go from B, and that is when you start again you start witnessing. So, in fact, I have drawn little bit incorrectly here, or rather I have exaggerated this. This would be more like this, and then so this B would be somewhere here. So, initially it goes into linear, the polarization increase is not massive, but when you go from B to somewhere around C, BC, this is basically P versus E is nonlinear region, and this is where polarization increase much more rapidly than what a linear relation would suggest, and massive increase in polarization happens. And once you reach point C, after that increases linearly. So, C to somewhere like D, when it saturates, there is a linear increase again. And then when you decrease the field, so after you have saturated, you have no more increase in the polarization that takes place. So, basically at very high fields all the dipoles are aligned, you have nothing else left to be aligned, and you will have very little increase in the polarization if you just increase the electric field by basically polarizing it more in terms of. So, electronic and ionic polarization will contribute, but it will be very small amount of polarization. So, basically it tends to saturation. Once it saturates, now if you start decreasing the electric field, so this is what you went about. Now, when you go back in this direction, what happens is polarization does not come back to 0, instead it stays as a value called as remnant polarization. What is the reason for this? Now, the reason for this, why the polarization follows a behavior A, B, C, D, and then why does it follow a path D, E instead of following D, C, B, A, is something whose regions lie in formation of what we call as domains in the ferroelectric material. And as we will see in the next lecture, these domains are basically regions of uniform, or rather I can write regions of single orientation of polarization. So, in these regions called as domains, which could be of certain shape, all the dipoles are aligned in one direction. So, this is a domain. It is not a grain boundary, it should not confuse with the grain boundary. The grain boundary is about the grain orientation, the crystalline orientation, whereas in this case we are not talking about crystalline orientation, we are saying that polar vector in these regions is aligned in one direction. Okay. So, we will come back to microscopic mechanisms of the switching in the next lecture, where we learn about domains, what domains are, and how do domain switching lead to what we see in reality. So, we will stop here. What we have discussed is about more details of phase transitions. We have finished the phase transitions, basically said that first order phase transition is because it manifested in sudden drop in polarization, sudden change in susceptibility, which is due to first derivative of free energy being discontinuous at Tc, whereas second order phase transition is manifested in gradual drop of polarization around Tc, it goes to 0 at Tc. Susceptibility also goes to 0 at 1 over chi goes to 0 at Tc, and it is in this case the second derivative of free energy is discontinuous, but first derivative is continuous. So, we will stop here, we will continue with the switching thing in the next lecture.